giving me the opportunity to present a plenary talk here. So indeed, under although you cannot really see it, it's almost useless anyway. The result of the first order elliptic system of operators or equations and the related spectral asymptotics. So here is the contents of my talk. First, we'll talk about first-order elliptic systems, what we mean by that in the geometrical and functional analytical background. Then we'll concentrate on the resolvent of such a system as such, and we'll look at the resolvent as a pseudo-differential operator, and we'll look for the principal and sub-principal symbols of this operator. And finally, we'll use this result for finding the first two, well, most importantly, the second Weyl coefficient in the spectral asymptotics of such a system. Let's begin with first-order elliptic systems. So what we have is a closed, by closed we mean compact and without boundary, connected smooth manifold of dimension higher than 1, and they will consider the half densities, smooth half densities on the manifold. Well, for the whole purposes of spectral theory, we can think of functions instead of half densities. The idea of using half densities in spectral theory is that spectral theorists mostly work with L2 and not LP. And in L2 you need an inner product, and this inner product is integration over the manifold with respect to a certain measure. So in order not to care about the measure, what we do is we simply work with half densities. When you multiply two half densities, you get a density, and you can invariantly integrate it over the manifold. So it's just a technical trick. For all purposes, you can think of half densities as functions. It doesn't change anything in nature. So then we'll consider pseudo-differential operators on the manifold acting on half densities. When we say that operator is of order D, a real number, if it's an operator from smooth densities to smooth densities, such that in any local chart, remember that the quantization and pseudo-differential calculus is invariantly defined only in Rn, but on manifolds, we define it in a way that the restriction to every chart or smooth densities compactly supported in a chart are given by the quantization of a certain standard symbol for classes, plus an infinitely smoothing operator, an integral operator with infinitely smooth formula. So we'll use the so-called Weyl quantization. Well, there are left quantization, right quantization, and then something in the middle, Weyl quantization, which has the following merit. When working on a manifold, again, as we said, the symbols, the full symbols are not invariantly defined. When you switch from one chart to another, your symbols do not transform covariantly. However, in Weyl quantization, the principal and sub-principal symbols do transform covariantly, and basically we have an isomorphism between symbols of order D up to symbols of order D minus 2 and operators of order D up to operators of D minus 2. So this interplay between the first two leading orders of the symbol and first two leading orders in regularity of the differential operator, they are in such a beautiful isomorphism, and that's all we need from them. And that's the reason we take the algebraically a little bit more complicated Weyl quantization as compared to the other ones. So in my notations, the AD is going to be the principal symbol and AD minus 1 the sub-principal symbol, and essentially the symbol is AD plus AD minus 1 plus a certain symbol of order D minus 2. All right, so, but now we are working not with scalar systems or scalar operators, but with systems, which means that my Hilbert space is that of square integrable m columns of half densities. And the inner product of two half densities of m columns is understood in the usual way. You take the Euclidean product of two columns, and then you get a density, and then you integrate it over the manifold, the standard L2 space. And I'll take, an operator A pseudo-differential operator, which is symmetric with respect to this inner product. And I work only with first order systems. So it's going to be a first order pseudo-differential operator acting on columns of half densities. And this operator is everywhere going to be locally equal to the quantization of its principal plus subprincipal symbol modular operators of order -1, d minus 2, d equals 1 here. So further assumptions that we make in this work is that we assume A is elliptic. And elliptic means, well, the principal symbol is everywhere invertible on the cotangent bundle aside from the zero section. And then we'll assume that the principal symbol has simple spectrum. So all eigenvalues are simple, again, aside from the zero section. Well, we can discuss what happens if we don't assume that towards the end of the talk, if time permits. Yeah, and then when most of the work is going to be done in local charts, local coordinates, and when working with the local point P, we'll write it as x, xi, where x is a coordinate and xi is the corresponding momentum variable. Right, so let's look at the A1. So A1 being the principal symbol of a formally self-adjoint operator, it is a Hermitian matrix valued smooth function on the cotangent bundle, and as such, at every point it has eigenvalues denoted by hj of p. These are going to be smooth scalar functions, and we enumerate them from, well, some of them are positive and some are negative. They never cross zero because we assumed that the operator is elliptic, so none of the eigenvalues can be zero. If they are positive, they stay positive. If they are negative, they stay negative. So we enumerate the positive eigenvalues with positive integers 1 to m plus and negative ones with negative integers from -1 to -m minus. So the m plus m minus is the full number of eigenvalues. It equals the dimension of the fiber m. Now, obviously, to every eigenvector hj, there corresponds the eigenvalue function bj, which is again a smooth function on the manifold, on the cotangent bundle. And we are also introduced the eigenprojectors pj, which project down to concrete eigenspace. Again, smooth matrix valued functions on the cotangent bundle. Now, every here and then we see this very fruitful confluence of classical mechanics, Hamiltonian dynamics, and microlocal analysis, where the principal symbols of elliptic operators are considered as Hamiltonian functions for a certain system of a point particle. And actually, it turns out that the Hamiltonian trajectories of this particle, considered as a mechanical system, describe the bicharacteristic variety of the operator in the sense of Hermander and Delstermark. So for every point in the cotangent bundle in local coordinates, xj and xij, the trajectory is given by the solution of the Hamiltonian equation. And it's not very critical, but at some point we'll refer to these solutions for a couple of definitions. So let's go now to the resolvent itself. So what is the resolvent? The resolvent is basically the inverse of A minus Z times identity. I won't write the identity operator for the sake of notations. So it is a pseudo-differential operator of order -1. It is the quantization of the symbolic inverse of A minus Z modular infinitely smooth operators. So we are interested in the principal and subprincipal symbols of this resolvent. Also, for the purposes of spectral asymptotics, we'll also be interested in powers of the resolvent. We'll see why a little bit later. And obviously, they're going to be the quantization of the Neuf power. Well, the Neuf power of the resolvent is a pseudo-differential operator with a symbol, the symbolic inverse power to the nu of A minus Z modular smooth operators again. So the first question that we ask ourselves, whether we can actually compute explicitly the Neuf power of the symbolic inverse of this symbol, A minus Z. And this is the first result, that the nu power of the resolvent is a pseudo-differential operator with a symbol given over there. Well, why this makes any difference? Because if you remember the composition law in Weil quantization of two symbols in the algebra of pseudo-differential operators, this isn't simply the product of two symbols. It involves all orders of the derivatives, both in space and cotangent space. So, and this trick where we don't compute actually this product with that rule, but rather take the derivative with respect to z to find the higher orders of the resolvent makes things dramatically simpler. And the second line is even more interesting, is that only the first two leading orders of the symbol of the resolvent is enough to compute the first two orders of the symbol for the nu power of the resolvent. This is not immediately obvious because we have derivatives in z. So it is not immediately obvious whether or not the remainder term of order d minus 2, when differentiated by z so many times, remains a remainder term of order d minus nu minus 2. And it turns out it is the case under some little technical assumption that we take z not everywhere aside from real line, but actually aside from the unit circle of radius 1, unit circle around the origin, and a certain cone with angular opening epsilon, and this epsilon can be taken as small as possible, just a technicality. Okay, and finally we need to compute the symbolic inverse of a minus z, and it turns out that it can be written in this form. Here the double Poisson brackets with 3 inputs is simply what's written on the very last line. It is your usual Poisson bracket, but now for matrix valued functions on the cotangent bundle. And you have the second input b not suffering any differentiation. It is just put inside in between two derivatives in the formula. This is a commonly used construct in spectral theory. Yes, so this gives you the first two leading terms of the symbolic inverse of a minus z. I want to mention that Victor Ivry obtained a similar formula for the last term. Well, the first two terms are more or less obvious. Everyone knows that they should appear. The third term has appeared in a paper by Ivry in '84, but it's written in a slightly different form. That these two are equivalent can be easily seen by simply using the Leibniz rule, because the Poisson bracket is basically double differentiation. But we'll see that this form, the form that we put it in, is computationally more convenient than Ivry's form. I'll come back to the history of the problem where Ivry plays a prominent role. All right. Now, for the reasons of asymptotic theory, we need to take the trace of a certain power of the resolvent. This is one of the most famous tricks in the theory. But in order to take the trace, this operator must be trace class. It can be shown that it is trace class. The power, nu power of the resolvent is trace class if and only if nu is larger or equal to n plus 1, n being the dimension of the manifold. So, and then when you compute the trace of the operator, it also, because this is an operator acting on, as a system acting on columns, taking the operator trace of the operator also involves in particular taking the matrix trace of the operator, which becomes a scalar pseudo-differential operator. So the first thing we do is we want to take the matrix trace of the nu power of the resolvent, and well, it is more or less clear that it should be written as the quantization of the trace of the corresponding symbol. However, it also turns out that it can be also written as the something involving the higher derivatives of simply the symbolic inverse of a minus z. So the symbolic inverse of the trace of the power minus nu can be written as certain derivatives of the symbolic inverse's trace. So we need to compute the trace of the symbolic inverse of A minus Z. So now let's do that. What you normally do, you have a Hermitian matrix or Hermitian matrix valued function. You decompose it using the spectral theory of Hermitian matrices as a linear combination of corresponding spectral projections, and the coefficients are exactly the eigenvalues. When you substitute this decomposition of the principal symbol into eigenspaces into this formula on the bottom, you get this formula. Here you see, again, the first two terms are more or less obvious. The first term gives you the principal symbol. The second and third terms give you the sub-principal symbol. And the second term, again, is called the obvious term, because everyone knew from the beginning it's going to appear. But the hard part is the third term, when you see there is a triple sum over the fiber indices I, J, and K. And there is a trace of Poisson, generalized Poisson brackets between the spectral projections. Note, however, that if I had used Ivry's formula, where is Ivry's formula? Is it here? Or is it not? Let's go sufficiently far back. No, it's not there. Somehow I'm skipping it. Ivry, where are you? Can't find Ivry. My apologies. Anyway, so what I want to say is when you substitute this formula into Ivry's formula, it has summation over 5 indices rather than 3, and it already becomes on this level. It already becomes much simpler when you use this representation rather than Ivry's one, and that's one of the reasons actually people didn't even seriously try to use Ivry's formula, because it immediately blows up in terms of number of terms you need to calculate by hand. All right, but the most important simplification comes actually from writing a formula for this trace, Pk, Pj, Pl. So it turns out that there is a magic identity, algebraic identity for this formula, and we found that the trace of this generalized Poisson bracket can be written in such a form when you see there are a lot of delta functions, Kronecker delta functions, so that the triple sum basically boils down to a single sum in all terms. And this gives you a compact and nice representation for the first 2 leading terms of the symbolic inverse of A minus Z. So again, the first term here represents the principal symbol, which was clear to everyone. The second term is part of the sub-principal symbol, but again, it was clear to everyone from the beginning. It's called the obvious term. The third term there is called is the so-called Safarov's term. I'll comment on that while we call it that way. And the last one is the curvature term. Again, I'll comment on that, why it's called that way. All right. So let's see what happens with spectral asymptotics related to that. So in order to do reasonable spectral theory, I need to assume that my operator is not just formally self-adjoint, but really self-adjoint. And it is with this H1 Sobolev space on half-density columns, so to speak. And since I'm working on a compact manifold, my spectrum is discrete. And it can be shown that the spectrum is semi-bounded from above, if and only if the principal symbol is a negative definite operator matrix, and vice versa. Generally speaking, we won't assume semi-boundedness for the system, and in a sense, the very meaning of this work is that we can study spectral asymptotics of the positive and negative parts of the spectrum separately. Right? Because for semi-bounded operators, there is a huge machinery involving heat kernel expansions and so on, which allow to compute many coefficients, but this only works for semi-bounded ones. One could think, why not take the square of this operator, get, say, a semi-bounded one, but the problem is when you take a square or do something else that reduces it to a semi-bounded one, then the two asymptotics get mixed, and you can't then disentangle separately the positive and negative spectral asymptotics, which are generally speaking they differ, and this is called spectral asymmetry. It does happen. All right. So we introduced the so-called counting functions. We enumerate the eigenvalues of this self-adjoint operator A by lambda k. There is the particular enumeration is irrelevant for our purposes, and the corresponding eigenvectors are going to be called Vk. We introduce the so-called local counting functions n plus and minus, which are, well, density valued distributions, so to speak. What they do, they basically count the number of eigenvalues. N plus counts the number of eigenvalues from 0 to a certain positive number lambda, and n minus count the number of negative eigenvalues from 0 to minus lambda. But the local counting function does this with certain weights, which are the norm squared of the eigenvalues. If you integrate it over the manifold, the eigenfunctions are normalized, so you get 1. And so the integral of this local counting function gives you the proper counting function, which simply tells you the number of eigenvalues between, say, 0 and lambda, positive or negative, respectively. So obviously, it's a step function as defined. And under certain technical conditions, namely that the point is non-focal, which means that basically a point in the cotangent bundle is called non-focal if the Lebesgue measure of all points in the momentum space out of which a closed Hamiltonian trajectory emanates is 0. Such points are called non-focal, and there is a classical result regarding this that uniformly for all non-focal points on the manifold, this bad, basically, step function still allows for two-term asymptotic decomposition as lambda goes to plus infinity, with a certain term which only known to nodes is to be O little lambda to n minus 1. And the coefficient C plus minus n minus 1 is the first Weyl coefficient, C minus plus minus n minus 2 is the second Weyl coefficient. So what one does in order to do better spectral asymptotics, you want to mollify this bad step function to get a smooth function so that it has better asymptotics. What you do is you take a Schwartz function, you take the convolution, it becomes smooth and nice. And then you have, again, another classical theorem about the spectral decomposition. A similar asymptotic decomposition works, but now we have much more precise remainder terms. So basically, the existence of this two-term asymptotics is established by classical means. The question is, can you actually compute these coefficients explicitly given the operator? So the formula for the first Weyl coefficient, the leading one, is known, and it's classical. So it is simply the volume interpreted in the sense that you take the, as I said, so the Hamiltonians Hj also are taken in as a kind of a Riemannian matrix, and in that metric you take the Euclidean volume of the non-Euclidean ball of radius 1, and this is a universal formula for the first coefficient. However, the second coefficient was pretty hard to obtain, and it was first obtained in 2013 in a pretty long and bloody way. And this is the formula, basically. In the first two lines, I've written it in terms of the eigenfunctions Vj. In the last two lines, I've written it in terms of the eigenprojections Pj. So again, the first term is the obvious term, which everyone knew is going to be there. The second one is Safarov's term, and the third one is the curvature term. And now it's time to say why those names. So I'll take you to the history of the problem. So in 1980, Victor Ivry produced a formula for the subprincipal symbol, for the second Weyl coefficient without proof. Then they realized it's wrong, and then in 1982 they produced another formula with a proof. I've put the proof in quotes because both the proof and the formula were unfortunately incorrect. And then Grigori Rosenblum, another big name in spectral theory, produced a similar formula in '83, which was again unfortunately wrong. In 1984, Victor Ivry came up with yet another formula without proof, but also an algorithm which, upon completion, would produce the proof for that formula. Unfortunately, the formula turned out to be wrong again, but the algorithm was correct. It's just that it was so hard to follow that algorithm. It involved computing so many terms that no one actually managed to do that for some more than 30 years, right? In '89, late Yuri Safarov from King's College produced one of the terms, namely the second term, and that's why we call it in their name. And finally, in 13, using a different method, namely the Levitin's wave equation method, in some more than 60 pages of rigorous computations, order by order approximations, and so on and so forth, they produced the formula in 2013. So, but with our principal and sub-principal symbols at hand now, we have a compact formula. We can actually follow the Ivry's algorithm very easily and produce the results. Namely, we want to take the trace of this operator. Well, we have a little technical problem, because if you take nu too high, then it stops being singular in the real line. It doesn't feel the spectral asymptotics anymore. If you take it too little, then it's not trace class. And there is a deficiency of 2 orders of derivatives there. So what we do is a trick. We substitute the 2 missing orders of derivatives by difference, right? This is the n-1th order differential plus 2 orders of discrete difference. It turns out to be exactly what we need. It's both singular on the real line, and it is trace class. So if we compute the trace of that expression, it turns out that once we already know the asymptotics exist, we want just to compute it. This method won't allow you to establish the existence of asymptotics. We take as granted that they exist because this has been proven by classical ways. We only want to compute them. From the existence of the 2-term asymptotics, we can derive this formula here with 2 B1 and B0 terms. And it turns out that the second value coefficient is simply this formula in the second line that takes the limit as phi goes to 0 from the positive side. And yeah, so let me come to the main results of this work. First, we found a formula for the symbolic inverse up to 2 leading terms, which is similar to Ivry's, but a little bit different, more compact. And then we have an approximation of the new symbolic power of the principle of the symbol of the resolvent. Again, not the strongest result of the work, because this trick with derivatives with respect to z for powers of the resolvent should have crossed minds of many mathematicians. So the most important part here is the magic identity for a trace pk, pj, pl, an algebraic identity that dramatically simplifies the algorithm, and you can immediately straightforwardly simply find what has been missing for some 30 years. And yeah, the compact formula for the trace of the symbol inverse, and finally an explicit formula for the coefficient. So, and yeah, this is all I wanted to tell you, and this is a reference to the paper where all this can be found in written form. Thank you.
Well, let's express our thanks.